Everything's school. Isomers made simple. Today we are going to make isomers feel much less confusing. The big idea is simple. Isomers have the same molecular formula, but a different arrangement. That means the same number of carbon atoms, hydrogen atoms, oxygen atoms, or other atoms can be connected or arranged in different ways. So by the end of this lesson, you should be able to look at two molecules and ask three questions. Do they have the same molecular formula? Are the atoms connected the same way? And do they have the same three-dimensional arrangement? Those three questions solve most beginner isomer problems. Slide 2. What students usually get wrong. A lot of students think that if two molecules have the same formula, they must be the same molecule. But that is not always true. A molecular formula only tells you how many atoms are present. It does not tell you how those atoms are connected. And it does not tell you how the molecule is shaped in 3 dimensions. For example, carbon 4 hydrogen 10 tells you there are 4 carbon atoms and 10 hydrogen atoms. But those atoms can be arranged as a straight chain or as a branch chain. Same formula, different structure, different molecule. That is the key idea. Slide 3. The big definition. Isomers are compounds with the same molecular formula but a different arrangement of atoms. The phrase same molecular formula means the atom count is the same. The phrase different arrangement means something about the structure or shape is different. For beginner organic chemistry, there are 2 major families. Constitutional isomers have different connectivity. Stereoisomers have the same connectivity, but a different 3-dimensional arrangement. Connectivity means which atoms are bonded to which atoms. So when you compare 2 molecules, first check the formula, then check the connections, then check the 3-dimensional shape. Slide 4. Formula versus structure versus shape. A molecular formula is the atom count. For example, carbon 4 hydrogen 10. A condensed formula shows groups in a shortened written form. For example, carbon hydrogen 3, carbon hydrogen 2, carbon hydrogen 2, carbon hydrogen 3. A structural formula shows how atoms are connected. A line angle formula uses lines and corners to represent the carbon skeleton. And a 3-dimensional drawing shows whether groups point forward, backward, up, down, or around a double bond. This is why formulas alone are not enough. The same formula can hide multiple different molecules. Slide 5. The main isomer family tree. Start with isomers. Isomers split into constitutional isomers and stereoisomers. Constitutional isomers have the same formula but different connectivity. The atoms are bonded in a different order. Stereoisomers have the same formula and the same connectivity, but different 3-dimensional arrangement. Under constitutional isomers, you often see chain isomers, position isomers, and functional group isomers. Under stereoisomers, you often see geometric isomers and optical isomers. Geometric isomers include cis and trans, and E and Z. Optical isomers include enantiomers and diastereomers. Slide 6. Constitutional isomers. Constitutional isomers are the easiest isomers to check first. They have the same molecular formula, but the atoms are connected in a different order. A quick way to say it is this. Same formula, different bonds. Chain isomers have a different carbon skeleton. Position isomers have the same functional group, but it is attached in a different position. Functional group isomers have the same formula, but different functional groups. The common mistake is only counting atoms and forgetting to check the bonds. Slide 7. Chain isomers, butane versus isobutane. Both butane and isobutane have the molecular formula carbon 4 hydrogen 10. Butane has 4 carbon atoms in a continuous chain. You can think of it as carbon, 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 carbon in a row. Isobutane, also called 2-methylpropane, has a branch structure. It has a central carbon connected to 3 methyl groups. The formula is the same, but the carbon skeleton is different. That makes them constitutional isomers. More specifically, they are chain isomers. Slide 8. Position isomers. 1-propanol versus 2-propanol. 1-propanol and 2-propanol both have the formula carbon 3 hydrogen 8 oxygen. They both contain an alcohol group, which means they both have an OH group. But in 1-propanol, the OH group is attached to the end carbon. In 2-propanol, the OH group is attached to the middle carbon. The functional group is the same. The carbon chain is the same length. But the position of the OH group changed. That makes them position isomers. Slide 9. Functional group isomers. Ethanol versus dimethyl ether. Ethanol and dimethyl ether. Both have the formula carbon 2 hydrogen 6 oxygen, but they do not have the same functional group. Ethanol is an alcohol. It has a carbon-oxygen-hydrogen pattern. Dimethyl ether is an ether. It has a carbon-oxygen-carbon pattern. Same formula, different functional group. That makes them functional group isomers. This is a good example of why the oxygen atom matters so much. Where that oxygen is placed changes the identity of the molecule. Slide 10. Stereoisomers. Stereoisomers are different from constitutional isomers. With stereoisomers, the atoms are connected in the same order. The difference is the three-dimensional arrangement. So the bonds are not changing. The shape is changing. This can happen around double bonds, inside rings, or around chiral centers. Geometric isomers happen when rotation is restricted. Optical isomers happen when molecules have non-superimposable mirror images or other three-dimensional differences. This is where students need to slow down and think in 3 dimensions. Slide 11. Why rotation matters. Single bonds can usually rotate. That means if 2 drawings only differ because one part rotated around a single bond, they may just be conformations of the same molecule. A conformation is a different shape made by rotation around single bonds. Double bonds are different. Double bonds do not freely rotate under normal conditions. That restricted rotation can lock groups into different positions. Rings can also restrict rotation. So whenever you see a double bond or a ring, ask yourself whether groups are locked on the same side or opposite sides. Slide 12. Cis and trans isomers. Cis means same side. Trans means opposite side. For alkanes, cis and trans can happen when each carbon in the double bond has 2 different groups attached. In cis-2-butene, the 2 methyl groups are on the same side of the double bond. In trans-2-butene, the 2 methyl groups are on opposite sides of the double bond. The formula is the same, the connectivity is the same, but the arrangement around the double bond is different. That makes them stereoisomers. More specifically, they are geometric isomers. Slide 13. E and Z isomers. Sometimes cis and trans are not specific enough. That is when we use E and Z. E and Z use priority rules to decide which groups are more important on each side of a double bond. The priority rules are called the Kahn-Ingold-Prelog rules. For an AI voice, say it like this: Kahn-Ingold-Prelog. The basic idea is simple. On each carbon of the double bond, identify the higher priority group. If the higher priority groups are on the same side, the molecule is Z. If the higher priority groups are on opposite sides, the molecule is E. A memory trick is this. Z means together because the high priority groups are on the same side. Slide 14. How to assign E or Z. Step 1. Look at one carbon of the double bond. Rank the 2 attached groups by atomic number. The atom with the higher atomic number gets higher priority. Step 2. Do the same thing on the other carbon of the double bond. Step 3. Compare the 2 high priority groups. If they are on the same side, the answer is Z. If they are on opposite sides, the answer is E. The most common mistake is comparing the wrong groups. Do not compare the biggest looking group. Compare priority using the atoms directly attached first. Slide 15. Chirality, the mirror image problem. A chiral object is not superimposable on its mirror image. Your hands are the classic example. Your left hand and right hand are mirror images, but you cannot perfectly place one on top of the other so every part matches. Some molecules behave the same way. They have mirror image forms that are not superimposable. This matters because the 2 mirror image forms can interact differently with biological systems. In organic chemistry, chirality usually appears when a carbon is attached to 4 different groups. Slide 16. Chiral centers. A chiral center is usually a carbon atom bonded to 4 different groups. The word usually matters because organic chemistry has advanced exceptions, but this rule works well for beginners. To check for a chiral center, find a carbon with 4 single bonds. Then ask whether all 4 attached groups are different. If all 4 groups are different, that carbon is a chiral center. If 2 groups are the same, it is not a chiral center. The common mistake is only looking at the first atom. Sometimes 2 groups both begin with carbon, but the rest of the group is different. Slide 17. Enantiomers versus diastereomers. Enantiomers are stereoisomers that are non-superimposable mirror images. Say enantiomers like this: Enantiomers. Diastereomers are stereoisomers that are not mirror images. Say diastereomers like this: diastereomers. Here is the simple comparison. If two molecules are mirror images and they do not overlap perfectly, they are enantiomers. If they are stereoisomers but not mirror images, they are diastereomers. For beginner exams, the key is to compare all chiral centers. If every chiral center is opposite, the pair is usually enantiomers. If some are opposite and some are the same, the pair is usually diastereomers. Slide 18. Meso compounds and racemic mixtures. A meso compound has chiral centers, but the overall molecule is a chiral because it has internal symmetry. Say meso like this: meso. Achiral means not chiral. Say achiral like this: I-chi-rule. A racemic mixture is a 50-50 mixture of two enantiomers. Say racemic like this: racemic. Meso compounds and racemic mixtures are not the same thing. A meso compound is one molecule with internal symmetry. A racemic mixture is a mixture of two different enantiomers. Slide 19. R and S. Configuration. R and S are labels used to describe the arrangement around a chiral center. To assign R or S, use the Kahn-Ingold pre-log priority rules. First, rank the four groups from priority 1 to priority 4. Priority 1 is the highest priority. Priority 4 is the lowest priority. Next, point the lowest priority group away from you. Then trace from priority 1 to priority 2 to priority 3. If the path is clockwise, the configuration is R. If the path is counterclockwise, the configuration is S. Counterclockwise. Slide 20. Worked example. Assign R or S. Imagine a chiral carbon attached to bromine, chlorine, a methyl group, and hydrogen. Bromine has the highest atomic number, so bromine is priority 1. Chlorine is priority 2. The methyl group is priority 3. Hydrogen is priority 4. Now place hydrogen pointing away from you. Trace 1 to 2 to 3. If the path goes clockwise, the center is R. If the path goes counterclockwise, the center is S. The most common mistake is forgetting to put the lowest priority group away. If priority 4 points toward you, the result must be reversed. Slide 21. Properties of isomers. Isomers can have different physical and chemical properties. That is because structure affects shape, polarity, intermolecular forces, and reactivity. For example, branching can affect boiling point. Changing the position of an OH group can change hydrogen bonding and reactivity. Changing an alcohol into an ether can strongly change chemical behavior. Stereochemistry can also matter in biology. Two enantiomers can interact differently with enzymes or receptors. The careful way to say this is not that all isomers are completely different in every way. The better idea is that different arrangement can lead to different properties. Slide 22. The exam decision tree. When comparing two molecules, use this order. Question 1. Do they have the same molecular formula? If no, they are not isomers. If yes, continue. Question 2. Are the atoms connected in the same order? If no, they are constitutional isomers. If yes, continue. Question 3. Do they only differ by rotation around single bonds? If yes, they are conformations. If no, continue. Question 4. Are they non-superimposable mirror images? If yes, they are enantiomers. If no, continue. Question 5. Are they stereoisomers but not mirror images? If yes, they are diastereomers. This decision tree is one of the best tools for exams. Slide 23. Common exam question patterns. You might be asked to identify whether two molecules are isomers. You might be asked to classify them as constitutional isomers or stereoisomers. You might be asked to draw all constitutional isomers for a formula. You might be asked to identify cis and trans isomers. You might be asked to assign E or Z. You might be asked to find chiral centers. You might be asked to determine whether a molecule is chiral or achiral. You might be asked to identify enantiomers and diastereomers. And you might be asked to assign R or S. The trick is not to memorize every possible drawing. The trick is to follow the same decision process every time. Slide 24. Practice round. Question 1. Butane and isobutane both have carbon 4 hydrogen. 10. Are they constitutional isomers or stereoisomers? They are constitutional isomers because the carbon skeleton is connected differently. Question 2. Cis 2-butene and trans 2-butene have the same formula and same connectivity. Are they constitutional isomers or stereoisomers? They are stereoisomers because the three-dimensional arrangement around the double bond is different. Question 3. Ethanol and dimethyl ether both have carbon-2, hydrogen-6, oxygen. What type of isomers are they? They are functional group isomers because one is an alcohol and one is an ether. Slide 25. Final recap. Here are the 3 questions to remember. First, same molecular formula. If not, they are not isomers. Second, same connectivity. If not, they are constitutional isomers. Third, same three-dimensional arrangement. If not, they are stereoisomers. That is the whole beginner strategy. Same formula tells you isomers are possible. Connectivity tells you constitutional isomer or not. Three-dimensional shape tells you stereoisomer or not. Once you learn to ask those questions in order, isomers become much easier. Everything School, simple help for confusing classes.